Hello everyone. My name is Leszek Mazurek. I'm the author of the paper which proves Collatz conjecture. I decided to record this video to explain my proof and present every step of the proof in the simplest possible way so people who are not professional mathematicians can understand it easily. You can download my paper from ResearchGate.net from the link presented at the screen. However, to understand even my explanation, there are few prerequisites needed. First of all, you need to have basic knowledge of arithmetic. You need to be able to think logically. And last but not least, you need to be familiar with binary notation. I will be using this binary notation in a proof. It's very important for this explanation. So what is Collatz conjecture? I believe that everyone who is watching this video actually is familiar with this problem, so we don't need to lose time to present Collatz conjecture here. Instead of that, let me say a few words about the method that I use in my proof. When processing numbers through the process described in the Collatz conjecture, we are landing at 1, but actually we are landing at a loop, which is constructed by numbers 1, 4, and 2. And that's the reason why majority of attempts to prove Collatz conjecture is based either on searching for another kind of loops or is talking about different cycles and analyzing their existence. However, it is not the case here. My method is completely different. I will be not talking about any loops or cycles here. So after this short introduction, we can start with the proof. Let's start from natural number and 0, which is in our case even. This number is even, we can divide it by 2, but we can do multiple divisions. So to combine all these divisions into one operation, we can just divide by 2 to the power p0 to get number n1, which is odd. According to Collatz process, odd number we should multiply by 3 and add 1 to it. In this way, we'll have another number n2, which is even, so we are again dividing it by 2 to the power p1 to get another odd number n3, and we are continuing this process multiplying by 3 plus 1, again dividing by 2 to the power, and so on until the moment when we have, in our case, number n8, which is even, so after division by 2 to the power p4, finally we've got 1. So that's basically an example of Collatz process. Every even number is divided by 2 to the power, and every odd number is multiplied by 3, and then also we must increase it by 1. We did this process starting from n0, and at the end we have 1. But we can do this process backwards. Starting from 1, we can progress towards number n0, making a reversal of every single operation. Our first operation will be reversal of this division by 2 to the power p4. To reverse this operation, we have to multiply by 2 to power p4. We've got number n8. At the bottom of the screen, we will reflect every single operation. As we started from multiplication 1 by 2 to the power p4, we will write it down at the bottom of the screen. As a next, we will reverse this multiplication by 3 plus 1. Doing this in reversal, we have to subtract 1 from number n8 and divide it by 3. So in this way, we are on the number n7. And again, we will reflect this operation at the bottom of the screen. Minus 1 divided by 3. Now we have to reverse next operation. In this case, this will be multiplication by 2 to the power p3. Okay. We've got number n6, and again we will reflect this operation at the bottom of the screen. And so on and so on. We will progress with our steps backwards, going up to the number n0. Okay, multiply by 2 to the power p0 equals n0. All this process starting from 1 up to n0 was reflected here in this formula at the bottom. Now we can simplify this formula by performing operations. As you can see, we are simplifying divided by 3, multiplied by 2 to the power p2, minus 1, okay, again divided by 3, again multiplication, minus 1 divided by 3 and last multiplication. So now we have this formula simplified, but we can simplify it even more by substituting all these sums like this. After this simplification, our formula looks like here. And please notice that all these m's have dependencies like presented. They are growing starting from m0. Every single one is bigger because we are adding additional p to the previous number. This m0 can be greater than or equal to 0. The reason is very simply, if it is 0, it means that number n0 is the same as n1, because this division is basically division by 1. Once again, m's are growing starting from m0 to m4, but this m0 can be greater or equal 0 depending on if our starting number is even or odd. Now we can make this bottom formula slightly more beautiful by adding here power 1, which doesn't change anything. And also we can add another multiplication by 3 to the power 0 to make it even more beautiful. Now, as you can see, we have nicely increasing powers of 3 to the power 0, to power 1, to power 2, to power 3, to power 4, which is important for this formula. So what we've got at the end is that our processing number n0 through Collatz conjecture till 1, we reflected into special formula, special representation of number n0, which means that if we can process number n0 through Collatz conjecture to 1, we can build this formula for number n0, this representation of number n0, and vice versa, which means that if we are able to represent this number n0 by such a formula, we can also be sure that this number can be processed by Collatz conjecture. We've got this formula. It was our specific case, but we can present universal formula for number n0, which looks like this. And here again, it's important feature of this formula is that powers of 3 are increasing step by step in this direction, and powers of 2 are just increasing, not necessarily step by step, in this direction. So as presented at the bottom. Again, with a remark that first power of 2, this m0 here can be in some cases equal 0 when this number is odd. We can present this formula in slightly different version by moving this power of 3 to the other side. Our formula looks like this, and it is exactly as I wrote in my paper in Theorem 1.1. If a given number n0 has a representation like presented, where n is natural number and all these m's is a sequence of integers, then Collatz conjecture is true for that particular n0 and vice versa. I believe that it was very clearly presented here, and of course you can check it on your own to verify again this formula that it is absolutely correct. I discovered this formula by myself, and only later I was informed that it is already known and described by two mathematicians, Bohm and Sontachi. In this paper, at the page 264, they stated in proposition 7 that the verification of Fermat-Ulam's conjecture can thus be brought back to the proof that each natural can be expressed in the form like this, which is exactly the same as formula on the previous slide. To be able to progress with my proof, I have to introduce one mathematical term, which is two-adic valuation of the number. Two-adic valuation of the number is usually represented by Greek letter nu of x. As stated here, nu of x designates two-adic valuation of x, which is how many times x can be divided by 2, of course within the natural numbers. In binary representation, we can check this example. Here, nu of 360 is 3 because 360 can be divided by 2 3 times. Have a look here, 360 and its binary representation, and we are dividing it by 2, which is 180, and binary representation again by 2, which is 90 binary representation, and last time by 2 we've got 45, and we are not able to divide it within natural numbers by 2 anymore. Here we have this 360 and its binary notification. As you can see, two-adic valuation of 360 is 3. And also what is important, and this will be used pretty often in my proof, that 2 to the power nu of x is the lowest non-zero bit in binary representation of x. So if we have this binary representation of our number, position of first non-zero bit from the right side is exactly this two-adic valuation. 2 to the power 3 is representing this bit. And also, it's pretty easy to understand because the place where this bit is located means how many times we can divide this number by 3. If we've got 3 zeros on the right side, each division is cutting 1 0. As you can see, number of zeros is decreasing and all zeros are disappearing here. So we can do this, in this case, 3 times. I hope now this two-adic valuation is clear, is very easy to understand. So once again, it tells us how many times x can be divided by 2, and 2 to the power nu of x is the lowest non-zero bit in binary representation of x. Now we are ready to progress with explanation of my proof. So we are going back to this formula explained previously. In my paper, I define special procedure how to get this formula for any initial number. So procedure 1, we are starting from step 1. We are selecting any initial number and defining ABC for this number. A will be 2 to the power p, where p is natural number. A0 must be greater than our initial number, so it's easy to get. B0 is just the difference between A0 and our initial number, N0, and C0 at the beginning is equal to 0. At this step, we can say that we have this equation between all this ABC and our initial number. So we are progressing to step 2. In step 2, we are just multiplying both sides of equation by 3. Using the following transformations. On the left side, we are just multiplying by 3. On the right side, A is multiplied by 4. B and C are generally multiplied by 3, but we need to do these additional adjustments to get this equation correct. As you know from the previous explanation, this 2 to the power nu of bi minus 1 is nothing else but the lowest non-zero bit of binary representation of bi minus 1. In this step, we've got our equation updated. On the left side, 3 to the power I multiplied by our initial number, and on the right side of this equation, we have ai minus bi minus ci. In step 3, we are just repeating step 2 in a loop, and this step 2 is repeated forever. Why this equation that we've got here is good for our proof? We can compare it to our required representation of initial number n0, and we see certain similarities. So on the left side, we are making this term always multiplying by 3. And on the right side, this is actually the most important part of this proof. ai minus bi at some point will be equal to the lowest non-zero bit in binary representation of bi, which will construct this term. And all remaining part of this required representation will be constructed in Ci. And it's easy to see because Ci is always multiplied by 3 from iteration to iteration, and additional bit is added to newly constructed C. So as you can see, in a few iterations, we are building this required increase of powers of 3, and each term is also multiplied by powers of 2. As as needed for this part. On the following slides, I will explain what's going on with all these terms when we are going iteration by iteration, how these terms are changing. To present it, I will use binary notation of numbers, like here, but to make it more precise and easier to read and understand, I will highlight particular bits by colors. I will be using green color for BI and this light green to reflect lowest bit of BI. And I will also use red color for AI as presented here. Actually, I will be not using digits, but only colors to reflect all these numbers, like this. AI will be always represented by a single bit. A0 is a single bit represented by 2 to the power p, and in each iteration, AI is multiplied by 4, which become another single bit. I can conclude that AI is always a single bit. That's the reason why there will be only one red square always present. I know also from this general formula for my iteration that AI is always greater than BI. So this red square will be always on the left side. Now I'm ready to define GI, which means gaps. So by gaps, I understand every zero, which is between AI and lowest bit of BI. So in this case, this will be just these 3 zeros. This is formal definition of GI. GI will be AI minus BI, so all this green, and minus, again, this lowest bit from BI. So this is formal definition of GI. And as a result of this operation, I will get just this highlighted by orange 3 bits here. And also this light orange means lowest bit of GI. After reshuffling this equation, I've got AI equals BI plus GI plus 2 to the power nu of BI. And from definition of procedure 1, we have this definition of BI, how BI is changing from iteration to iteration. When I substitute for AI into this equation, I've got this and finally this formula. This formula is very important and will be used in following presentations. That's the reason why I will keep it visible on the screen all the time. Based on this formula and my highlighted bits here, as presented, AI is in red, in green BI with a highlighted lowest bit of BI. Then in orange, GI, again with light orange, lowest bit of GI. I will go from iteration I to iteration I plus 1. First of all, I need to multiply BI by 4. It means that I need to shift whole BI by 2 positions to the left, as presented here. As you can see, I'm shifting BI together with all gaps. And as you remember, AI is also multiplied by 4, so I shifted this red square 2 positions to the left. And now I have to add GI. I'm adding these 3 bits here to my shifted BI. And when I sum up, I've got this new BI with new gaps. Because when I sum these bits together, some new gaps appear in my BI plus 1. Now we will check how GI grows, what's going on with GI. From definition of GI for iteration I plus 1, we have this formula. And from definition of AI for iteration I plus 1, we have 4 times AI. When we will substitute this BI plus 1 and AI plus 1 in this formula, we've got something like this. And after simplification, we can substitute AI minus BI to get this. And finally, we've got formula how GI grows. So we will also keep this formula visible on the screen. We can say that this formula that we've got here for the growth of GI is not the best one, because it is not only dependent on the previous iteration, GI and BI, but also it is dependent on the result of BI plus 1 and its lowest bit. This formula is not the best and we will try to improve it. We have to consider 3 different cases. Case 1, when two-adic valuation of GI is greater than or equal to two-adic valuation of BI plus 2. what does it mean? It means that lowest bit of GI is at least 2 positions to the left from the lowest bit of BI. As presented here, you can see it here that this light orange color here, which means lowest bit of GI, is 2 positions to the left from lowest bit of BI. Here again, we are multiplying by 4 and adding GI to get new BI plus 1. Okay, let's check another case. Here we've got only one bit in GI, and again we are multiplying by 4, which is shift 2 positions to the left of BI, and we are adding GI, here only one bit. So that's the result of our BI plus 1. Let's check another case. Here the lowest bit of GI is 3 positions to the left from lowest bit of BI, and that's the result after shifting BI 2 positions to the left, which reflects this multiplication by 4. We are again adding GI to get new value of BI plus 1. We can summarize all these 3 examples by saying that the position of the lowest bit of BI plus 1 is greater than or equal to the position of the lowest bit of BI plus 2. We can see it in every single example here that position of the lowest bit of BI plus 1 is shifted to the left at least 2 positions from the position of the lowest bit of BI. So we can observe it here and here and here. Based on this result, we see that this term that we have to subtract at the end here will be greater than or equal to this term that we have to add here. We see that in case 1, GI plus 1 will be less than or equal to 3 times GI. Once again, position of the lowest bit of BI plus 1 is always shifted at least 2 positions to the left from the lowest bit of BI. And because of this term will be greater than or equal to this term, and GI plus 1 will be less than or equal to 3 times GI. This will conclude case 1. Case 2. In case 2, we've got situation where lowest bit of GI is shifted 1 position to the left from lowest bit of BI, and GI is greater than its lowest bit. Here we have this case. Lowest bit of GI is shifted just 1 position to the left from lowest bit of BI, and GI has more bits, is greater than its lowest bit, which means that there is additional bit on the left in GI. After this operation, we are multiplying BI by 4 and adding GI, so we are shifting 2 positions to the left BI and adding this GI here. After summing up, that's our result. Let's check another case. Here is very similar case, but this another bit in GI is closer. We've got again multiplication by 4, and we are adding our GI to get the result. In this case too, based on these examples, and I really recommend to check more examples, conclusion is that lowest bit of BI plus 1 is shifted 1 position to the left from lowest bit of BI. We can see it here and here. From this result, we are referring to our general formula for growth of GI, and you can see we can substitute this new of BI plus 1 here in this term. So we've got this, and after this subtraction, we can simplify it to the form like this. As we see here, nu of GI equals nu of BI plus 1, which is exactly what we got here. We can substitute to this formula, but we know from here that GI is greater than 2 to the power nu of GI, which means that GI consists of at least 2 bits, which means that 2 to the power nu of GI is less than or equal 1/3 of GI. If GI consists of at least 2 bits, it means that its lowest bit is less than or equal to 1/3 of its total value. From this, we can summarize this case that gi plus 1 is less than or equal 3 and 1/3 of gi. This will conclude case 2. Now we can progress to the third and the last case. In this case, we have lowest bit of gi is shifted one position to the left from lowest bit of bi, but in this case gi is equal to its lowest bit, which means that this gi is just a single bit. The situation described in this case is presented on this picture. We see that after multiplication of bi by 4 and after adding gi, we've got this bi plus 1, which, as we can easily see, gi plus 1 is equal 4 times gi. It is shifted 2 positions to the left. But also in this case, we can see that in the next iteration, when we will go from bi plus 1 to bi plus 2, we are multiplying bi plus 1 by 4 and adding gi plus 1. We've got bi plus 2, but in bi plus 2 there are no any gaps, so it means that gi plus 2 will be equal 0. So we can summarize this case that in case 3 gi plus 1 is equal 4 times gi, but then gi plus 2 is equal to 0. So from all these three presented cases, and there is no other case possible, we can conclude that gi plus 1 is equal a times gi, where a is less than or equal 3 and 1/3, or a is equal 4, but then gi plus 2 is equal 0. We can replace this formula presented here for growth of gi with our newly received formula described here. We can see now this formula that we've got here for the growth of gi is much simpler and more beautiful than previous one. We check gi plus 1 over bi plus 1. We can easily see that it will be equal a times gi over 4 times bi plus gi, where a is less than or equal 3 and 1/3. What does it mean? It means that gi plus 1 over bi plus 1 is less than or equal 5/6 times gi over bi, which means that limit of this term is equal 0. And of course we have still this a equal 4 at the bottom. So we have to say or when a is equal 4. 2 iterations later we have gi equal 0 as presented here, which basically means that gi to bi is equal 0. Now we can extend this limit adding 1 to it, which will be bi over bi. And the same we will do on the right side. And we will substitute for bi plus gi from our general definition of gi. So after substitution, we've got limit ai minus lowest bit of bi over bi is equal 1, or ai minus lowest bit of bi over bi is equal 1 without the limit. We have either this or this. Now we can do few very simply transformations on the right side here, just to see that in case this term is exactly equal to 1, we have another very similar term, which is basically equivalent of this one. We are progressing with our transformations to see that in both situations here, we have actually the case where there are no any gaps, and ai is equal to bi plus its lowest bit. When we will add this lowest bit here, all these bits will collapse to ai. Now we will quickly check if the fraction ai over bi has a limit. So as we know so far, ai is growing always multiplied by 4, and bi is growing always multiplied by 4, plus gi is added to the newly created bi. As we can see, this fraction will be decreasing when gi is greater than 0, or this fraction will be fixed when gi is equal to 0. we know also that AI is always greater than BI for all I. So we can say that fraction AI over BI is decreasing as I is growing, or AI over BI is fixed on its limit. But definitely from this we can conclude that a limit of AI over BI exists, and this limit is greater than or equal to 1. So as we know that this limit exists, we can do the following transformations. We could split this limit into 2, and finally we know that this limit is equal to 1 plus this limit. Now we will evaluate such term. I received some comments that I'm not allowed to evaluate this limit because I don't know if this limit exists. It is not true because, for example, I can say easily that whatever this term means, it is equal to this term, and this will be correct. So as presented here, I can evaluate this term just to check if this limit exists or not. So I can continue this evaluation as long as I will keep both sides of this equation equal. What is on the left side will be equal to the thing which is on the right side. Everything is fine, and I can evaluate this term. I can continue this evaluation. So now instead of this 1, I can put BI over BI, which is obviously 1, and I can do this transformation switching BI with AI. This is exactly the same as above. Now, as I know that limit of AI over BI exists, like here, I can extract this limit from this term, and I can also put exactly this limit from here into this equation, because I know that it exists and its exact value. So what I did here, now I'm doing normal mathematical multiplication. I'm multiplying this term by these both terms, so that's the result. Let's move this equation to the top of the screen and continue with explanation. So as you can see, at the end of this equation, we have very interesting term, which is multiplication of two limits of the inverted values. So what we can say about these terms? So we can say that 2 to the power nu of bi is always greater than 0. Bi is always greater than 0. Bi is greater than or equal to its lowest bit. So we can conclude that this term is greater than 0 and less than or equal to 1. So let's talk for a while about these limits. What does it mean that we are increasing this I to infinity? It simply means that we are changing I step by step into direction of infinity forever. Infinity is not a number, it is a kind of direction that we are increasing our I step by step towards 2. Let's present it in a vertical way. So here we increasing I into direction of infinity, which means that we are changing I iteration by iteration, step by step, to I plus 1, I plus 2, I plus 3, and so on. But it also means that I is changing through exact values into direction of infinity. As I said, infinity is not a number. For every single exact value of I, we have exact values in both terms, in both sequences, this sequence and in this sequence. So we've got exact values for I, we've got values for I plus 1, values for I plus 2, and exact values for I plus 3. And for every pair of these values, a result of multiplication of them is always 1. Here is 1, here is 1, here is 1, here is 1, and so on to infinity. As we see, for every exact value of I, for every exact value of I, a result of multiplication of exact values in both sequences is equal 1. We can say that this limit multiplied by this limit for every exact j is equal 1. So we can substitute this term by this proposition, which means that for every exact value of j, here we've got 1, and we are just changing this j to infinity. But for every exact value, this will be 1. This will be always 1. It's easy to see that limit of this term is 1, so we can, instead of this limit, we can put here 1. And of course, based on normal mathematical rules, now we can move this term to the other side. From this equation, we can conclude that both of these limits must exist to make it possible that their difference is equal to 1. And we can also simplify to this form, which is our result. Let's go to our previous slide with this result to present it as a conclusion. After logical transformations of this limit, we concluded with this limit. Please notice it is very similar to our right side. What is presented on the right side describes situation in case of exact values, and here we've got limits. If we've got this limit, we can say therefore such iteration n exists that for I greater than or equal this number of iteration, this term will be less than 3. If this term is less than 3, so it means that AI minus BI is less than 3 times lowest bit of BI. As you probably remember, we had definition of GI, the form like presented here at the bottom. We can substitute AI minus BI from this equation to get this, and finally this result. GI is less than the lowest bit of BI multiplied by 2, which means that it is less than the bit which is next to the lowest bit of BI, like here. It means that GI does not exist. GI is equal 0. So again, from this equation at the bottom, we can conclude that here we've got AI is equal BI plus 2 to the power nu of BI, which is its lowest bit. So we've got exactly the same equation as we've got here on the right side. And we've got situation which is presented here on this picture. We can conclude this whole analysis with a statement that such iteration n exists that for I greater than or equal n, AI minus BI is equal 2 to the power nu of BI, which is exactly what we promised to achieve, what we needed for our required representation of n0. So once again, when we are running proposed procedure, we are multiplying our initial number always by 3 to get this term, and after number of iterations we've got AI minus BI equal 2 to the power nu of BI, which is the lowest bit of BI. There are no gaps in BI, which is this term, and all remaining terms are created in CI as needed for our required representation of our initial number n0, which basically proves that for any n0 we can make this representation using my procedure, which proves that any n0 selected at the beginning can be processed to 1 by procedure proposed in the Collatz conjecture, which proves Collatz conjecture. Now I will present procedure 1 from my paper in practice. I will do this using specially prepared Excel sheet together with procedure 1 implemented as a macro. Here you have this Excel. I will briefly explain what you see on the screen, and in a moment I will show how this procedure works. In cell A1 we have our initial number. Below we see all odd numbers when processing 27 to 1. It has nothing to do with our procedure, it's just for comparison normal Collatz process. Then here we have number of iteration, so starting from 0, increasing numbers. Then we have 3 to the power I multiplied by our initial number, and AI, BI, CI from procedure 1 together with GI and 2 to the power nu of BI, line by line, iteration by iteration. In these 3 columns we see GI plus 1 over GI, BI plus 1 over BI, and CI plus 1 over CI. On the right side, we have binary representation of each iteration, line by line. At the top, we have powers of 2 with corresponding values, and here we've got our bits as described in the paper. Please keep in mind that because of limitations of Excel, higher bits are on the right side here, and the lowest bits are on the left side. As you can see here in this row, we see how iteration by iteration all bits are changing. So let's start from our AI. As we can see, AI from iteration to iteration is jumping 2 columns to the right. In green we have BI, so let's check it value by value. So for example, in this first row, we have bi equal 5 because of this bit, which is 4 to the power 2, and this bit, which is 1 to the power 0. So this is our bi in the first row. And of course, you can check row by row what is here in a column bi is sum of all these green cells on the right side. The same situation is with gi, which is calculated as a sum of all bits. As you can see here, we've got 26 in gi, and it's just a sum of 16 plus 8 plus 2, which is 26. So in case of GI, it is also just a sum of all highlighted in this color bits. How CI is calculated? For CI, I've got all these numbers, which means powers of 3. And as you remember, in CI, we have powers of 3 multiplied by powers of 2. So powers of 3 are represented by these numbers. Powers of 2 are represented here at the top. So for example, this cell means 3 to the power 4 multiplied by 2 to the power 4. Okay, let's check another example. So this one, the meaning of this cell is 3 to the power 2 multiplied by 2 to the power 5, and so on and so on. For every cell, we've got multiplication. It's one remark. As a consequence of this macro, 0 is represented by minus sign here. So for example, here we've got 3 to the power 0, which is 1, multiplied by 2 to the power 7, Here at the top, we have a result generated after macro is executed. So for example, let's start from very simply case. Let's say we will start from 15. As you can see, only in normal Collatz, which is generated automatically row to row, it has nothing to do with our macro. Now I'm starting macro. Okay, macro was executed. Here we have a result. A result is in a form described in the paper. On the left side, we have 3 to the power 5 multiplied by our initial number, which is 15. And on the right side, we have different multiplication of powers of 2 by powers of 3. Powers of 3 are increasing in the right direction. So here we have 3 to the power 0, 3 to the power 1, 3 to the power 2, 3 to the power 3, and 3 to the power 4, while at the same time powers of 2 are increasing in opposite direction. 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 8, and finally the biggest 2 to the power 12. So that's the result. You can quickly check if left side is matching right side. So I will copy. Left side is this number, and right side okay, as you can see, numbers are the same, so it means that 15 can be represented in this required form as presented here. Above, I created also a LaTeX version of this result. Let's check slightly more complicated case, which will be 27. As you can see, macro is executed. And here we have our result. I can recommend for verification of these big numbers, it's good to use full precision calculator, which you can find on the internet. So I will check quickly this result. It's a pretty big number. As you can see, it seems that left side is equal to right side here as well. Let's talk a little bit what's going on in this macro, and we can check this binary representation. I will zoom it out a little bit just to show you what is the goal of this macro. Here we have this AI, which is growing like 4 multiplied always by 4. So we have this line. And here we have edge of our GI, which is growing like 3 1/3. So we can draw it here. And here there are no more gaps, starting from here, from this point, which means that PI is continuous, all beats without any gaps. And that's the end of our process, we can select this row. The result of this procedure is corresponding to normal Collatz on the left. And also here in GI column, exactly at this row, GI is 0. I will make it bigger. GI is growing. Here numbers are growing, but at some iteration suddenly become 0. Gaps are disappearing, as you can see here on the right side. So here there are no more gaps. This is BI, this is AI, and no more gaps since this point. So we can check another example. Okay, it's rather short. And again, on the right side, there is a moment where there are no more gaps. Now I will try to generate a little bit longer example. Okay, so as you can see, it's many more numbers in this process. Okay, we should wait till macro will execute till the end. Okay, it's done. Here is the result. Very long representation. It's starting from 2 to the power 107. I will zoom out to show you that here on the right side, we've got a moment where, again, gaps are disappearing. Here you can nicely see that this AI is growing like 4, jumping from iteration to iteration 2 beats forward. And GI is growing like 3 1/3, which is less than 4. That's the reason why the slope is different. And here is a critical point where there are no more gaps. And it is always like that, as I prove in my paper. What is in a violet color here? GI plus 1 over GI. As you can see, in every row, this number is less than 3 1/3, as it was presented in my paper. I want to show one more thing. So that's another example for number 9. As you can see here, normal Collatz, and our result of our procedure is in this line. So what is taken to this result is exactly this row. And as you can see, here is this lowest bit of BI, which is first here. It's like 2 to the power 13. And then all these blue cells representing all multiplication of powers of 2 and powers of 3. But even so, it is reaching 1. According to Collatz, we can still continue procedure 1 from my paper. What will happen if we will continue this procedure? As you can see here, we can get another result and another representation of our initial number using another values. And we can continue with another result and another result and another result. All these results are correct results for required representation of our initial number. These are the results for number 9. As you can see, this is our first result, but when we will continue this procedure 1, we will get another representation which is also correct and another representation which is also correct. The fact that we are not stopping this procedure but we can continue its execution means that, as stated in Theorem 4.1 in my paper, for every initial positive integer n0, an infinite number of equations exist that satisfies Theorem 1.1, which is our required representation of this number. We do not have just one representation, but we can have many of them. Infinity, many of them. Here you have results presented previously during this presentation. You can check them carefully on your own. Another one, as you can see, this rule that powers of 3 are increasing in one direction and powers of 2 are increasing in another direction is always present. Here at the top you have exact values of right side and left side of this equation. Last one. If you want to check on your own how my procedure works, you can download Excel presented in a second part of representation from this link and play with it, running procedure 1 for different numbers and checking carefully what's going on. If this presentation was helpful for you, you can also buy me a coffee at this link. Here you have also links to some other papers available to download at ResearchGate. Collatz Conjecture, there is also a paper about division by zero and general relativity theory of numbers. Thank you very much for watching. I believe that my video was not too complicated and you were able to understand fully Proof of Collatz Conjecture. Thank you very much.